We have some homework from last night, page 665, 7 to 11. We're going to check over 3 of those questions, specifically 8, 9, and 10A. Question 8 says a 4 centimeter high object is located 10 centimeters from a concave mirror. I'm going to circle this. Let's say F is positive value. If I forget to do that, it's not the end of the world in this case because it is a converging mirror, a concave mirror. In the end, that makes F positive. If I forget to make F positive, then it's going to be positive by default. When it's really important is that when you've got a diverging mirror that you remind yourself that F has got to be a negative value. I like to put it down all the time because I find if I do it for every question, then I'm less likely to forget to do it when it really matters, right? When it becomes a negative value. So I'm going to say concave mirror, converging mirror is a positive value of F. I've got characteristics of an image here, and I've got the height of the image. We want to find the focal length. I don't think I actually need the characteristics here for this question, but if I do, I'll use them here. What do I got given to me here? Object is 4 centimeters high. That's HO, 4.0 centimeters. The object distance is 10 centimeters. Now, it doesn't tell me whether it's a real or virtual object, but we know that for us in physics 30, it's always going to be a real object. So we're going to make it positive 10 always. The image is produced 5 centimeters high. HI is going to be 5 centimeters. It's right side up. Oh, it is important, okay? It's right side up. If the image is right side up, then HI is going to be a positive value. If it was upside down, then HI would have to be a negative value. So it is important to know. We want to find the focal length here. I don't think I need to know that it's virtual, but they add it, whatever. Define this. I want to say 1 over F is equal to 1 over DO plus 1 over DI, but I got a problem here, and that is that I don't know what DI is. Anybody make a suggestion as to how I might find the value of DI here? Yeah, see? Yeah, we know that M is equal to HI over HO, but HI over HO is equal to negative DI over DO. I know what HI is and HO is. It's 5 over 4. 5 over 4 is equal to negative DI over 10. And I think DI works out to be here, I think it's negative 12.5. Is that right? Well, now we can do this, right? 1 over F is equal to 1 over 10 plus 1 over negative 12.5. By the way, if the negative's on the bottom, it's the same thing as saying the negative's on the top, right? Doesn't make any difference where you put it. Let's do this on the calculator, you know. Let's say 10x to the minus 1. Let's subtract, because really when we add a negative value, we're subtracting, right? So subtract 12.5 x to the minus 1. Let's press enter, and then let's press enter again. That gives me 50 for the focal length here. Oh, we got a positive value for the focal length, right? Should we have? Yeah, we predicted that we would, right? It's a concave mirror, a converging mirror. We predicted it would be a positive focal length, and sure enough, it was. Yep. Yeah, if you get a negative value, I mean, that's the nice thing about telling us that it's a concave mirror. We didn't need to know that it was a concave mirror here, right? With the information we were given, we could solve this question without knowing that this is a concave mirror. But when they tell me it's a concave mirror or converging, and we get an answer that's positive 50 for focal length, it's a nice way to check. It increases dramatically the chances of me being correct, right? If I get a negative value for F, we know that we're wrong, because it needs to be positive. Now, if we get positive, it doesn't mean we're right, but it means the chances of being right are greater. All right, number 9 has 3 questions. In number 9, we want to draw a ray diagram for a converging mirror in 3 different scenarios here. Let's draw the first one here. There's my converging mirror. This is F. This is going to be 2F. We're going to draw the object this time at 2F, or the center of curvature. First ray is going to go parallel to the principal axis, then down through the focal point. Second ray is going to go down through the focal point, or somewhere near the focal point. Let's pretend that went through the focal point. And let's pretend that was straight. And let's pretend it ended up directly below 2F. What are the characteristics of this? It's same size, it's inverted, and it's real or virtual. Real solid lines are intersecting there. What if we move our object a little bit? Here's my mirror again. Here's F. Here's 2F. This time we're going to put it way, way in here. This is really close. Remember, this is the guy, the picture that I showed you when we first introduced this lesson. Picture of the guy looking in the mirror, seeing this massive right side up image of himself. First ray, parallel down to the focal point. Second ray is going to go as if it's away from 2F and then back upon itself like this. Should go through 2F. You're using a ruler, right? Okay, on a test, of course, you can use a ruler. Extend those back because they don't intersect on that side. You find that they intersect over here. What do you see? Larger, upright, and virtual, which is exactly what we would have predicted based on that picture that you saw the other day on, again, the first day we introduced this. And at 3F, all right, now we're going to move it way out here. Here's F, here's 2F. We're putting our object way out here. First ray, parallel through the focal point. Second ray through the focal point, parallel. We get an image right here that's formed smaller, inverted, and real. We're good there? In number 10, draw a ray diagram for a diverging mirror. Diverging mirror, F is a negative value. Although we're not doing a calculation here, so it doesn't really matter. Habit, right? 0.5F. So let's say we've got our diverging mirror, our convex mirror. The focal point is actually on the other side of it. We're going to put our object really close to the mirror right here. First ray is going to go parallel and then away from the focal point. Second ray is going to go down toward the focal point, but then it can't make it that far because of the mirror. Extend the reflected ray, and my image will be formed right here. Now, the other two of these are going to end up being the same, right? The image might be a little bit smaller, a little bit bigger, but it's still going to be smaller than the object. It's still going to be upright, and it's still going to be real or virtual. Virtual. Dotted lines intersect. You want to see this? You can, but you can't project it onto a screen. You got to look into the mirror to see it. Yep. Yep. Good. Yesterday we moved forward a little bit and started talking about refraction. We defined refraction loosely as the bending of light when the light goes from one medium to the other. When light goes from air to glass, it changes direction. It bends. When it goes from water to air, it changes direction. It bends. Why does it do that? Well, when light goes in at an angle other than straight on, because of the change in speed, and we know the speed will change, right? When light goes from one medium to the other, the speed changes. If it goes in at an angle, that change in speed will cause a bending phenomenon to take place. That's refraction. In Physics 20, if you were in my class, I gave you a little bit of an analogy to help you to understand why light or why waves will bend when they go from one medium to the other. Let's say we've got a paved parking lot here. And over here we've got a swamp. It's a swamp where the water is, I don't know, 1/2 meter deep. Hey, you can stand in that swamp and you don't go underwater, but part of your body is underwater. You can walk in it, but obviously can't walk in it quite as fast. For whatever reason, we got soldiers marching in this parking lot. I'm not sure why, but let's say that we do. Okay, there's a whole row of soldiers marching in this parking lot. If we look at them from above, then these soldiers might look something like this. Now, a few seconds later, let's say 5 seconds from now, those soldiers who are marching this way are not in the same position, right? You know what soldiers do though, right? They all march in stride, right? So if one soldier has gone up a certain distance, then the other soldiers are going to go up the same distance, right? So five minutes later, these soldiers are all like this, right? Except for this guy and this guy. This guy hasn't gone quite as far. This guy has gone even less distance. How come? Because the water, you can't go as fast in the water, right? When these soldiers marched from the pavement to the water, they slowed down. They can't walk as fast in water as they can on pavement. 5 minutes later, soldiers are up here. Now this guy is now in the water, so he's going slower too. This guy's still in the water. This guy's still in the water, so they're going slower again. And again, 5 minutes from now, this guy's in the water now. This guy's still there. This guy's still there. This guy's still there, and this guy's still there. What does it look like from above? Looks like this. The wave was going straight up, and now the wave is going this way. Due to these soldiers changing speed when they went from one medium to the other, their direction also changed. That's refraction. Okay? Light undergoes refraction. Light, when it goes from one medium to the other, will bend. It will change directions, and it does that because the speed of light either decreases or increases depending upon whether it's going from a medium with a high index of refraction to a low index of refraction. So what's index of refraction? Well, kind of in everyday thinking, we can think of it as how much light bends when it goes from one medium to the other. How much light bends. But the true definition of index of refraction comes back to a little equation that I gave you yesterday. It's the ratio of the speed of light in a vacuum, which is always, by the way, 3 times 10 to the 8 meters per second, to the speed of light in the medium. So if you're looking for the index of refraction of medium 1, then it would be c over the speed of light in medium 1. Now, what's the maximum possible value for V1 there? What's the maximum possible value for V1? 3 times 10 to the 8 meters per second. Okay, if we're in a vacuum, then the speed of light in a vacuum is 3 times 10 to the 8, and the speed of light in that medium is 3 times 10 to the 8. If you're in air, the speed of light in a vacuum is 3 times 10 to the 8. The speed of light in air is to 3 digits, still 3 times 10 to the 8. So the index of refraction would be 1. But if you're in water, the index of refraction is, the speed of light is about 2 times 10 to the 8. 3 divided by 2 is 1.5. The index of refraction would be 1.5. If you're in cubic zirconium, you know what cubic zirconium is? It's like fake diamond. Okay. Speed of light slows to about 1.5 times 10 to the 8. So it slows down pretty dramatically. Okay, the index of refraction would be about 2. In glass, it's 1.5. In cubic zirconium, it's about 2. That means light would bend more in cubic zirconium because the index of refraction is greater. Now for diamond, it's about 2.4. So light bends even more in diamond than it does in air. And you're going to see why early next week, how that explains, in part at least, why diamonds sparkle so much more than glass sparkles, or even more than cubic zirconium sparkles. Index of refraction, a measure of how much light bends in the medium. It is the ratio of the speed of light in a vacuum to the speed of light in that medium. Now, we said yesterday that the index of refraction is different not only for each medium, but it's different for each color. If we have a glass prism here, generally we say that the index of refraction would be about 1.5. But it's actually slightly different depending upon the color. On average, maybe it's 1.5, but it might be 1.497 for red light, and it might be 1.503 or something like that for violet light. The index of refraction for the material is a certain value on average, but it's different for each color. Why? Well, because red light, when it goes into the new medium from air to glass, it slows down, just the same as violet light does, but it doesn't slow down as much. Violet light slows down more when it goes from air to glass. Therefore, the index of refraction for this glass is bigger for violet than it is for red. If it slows down more for violet than it does for red, then the index of refraction is higher for glass for violet than it is for the glass for the red light. Now, you can imagine on the other side, if light slows down more for violet when it goes into the glass, it's going to speed up more when it goes back into the air, right? Again, that's because the index of refraction for glass is more for violet than it is for air, because we get a bigger difference in speed, a bigger change in speed. All right, so what do we find? White light comes into this, hits this boundary between the air and the glass, and that white light splits up. It disperses because there's a different index of refraction for each different color. Red light would have the smallest index of refraction. Actually, I didn't say that right. Red light does not have the smallest index of refraction. Glass has the smallest index of refraction for red light. Glass has the largest index of refraction for violet light. It's not the light that has the index of refraction, it's the glass. But it's smaller in glass for red because red light bends less because the speed changes less. It's bigger in glass for violet because the angle becomes bigger, the change in direction is more because the change in speed is more for violet light. What do we get on this side? We get this continuous spectrum. We call that a continuous spectrum because it's not like you get one band of red and then one band of orange and so on. The red transitions into orange, which transitions into yellow and so on. You don't have distinct colors. It's literally a rainbow where it transitions from one color to the next, continuously, as opposed to discretely. Does that make sense? All right. I want to give you an equation right now that describes how much the light is going to bend. Like, which color produces a bigger index of refraction? Which material will cause light to bend at a higher angle? Which material will cause light to slow down the least? The equation that I want to give you is called Snell's law, and it looks kind of ugly, but it's actually not that bad. There's 4 parts to it. You only ever need to use, of course, 2 parts. In any equation that you're using, you're only ever going to have one set of equal sign, right? So it's going to be sine theta 1 over sine theta 2 equals V1 over V2, or it might be V1 over V2 equals N2 over N1, or it might be lambda 1 over lambda 2 equals N2 over N1, whatever. 2 parts of this equation. What do these different variables mean? Let me draw out a picture here. The solid line is my boundary between the 2 materials. The dotted line is the normal line. The line drawn at 90 degrees, that imaginary line. Let's say we've got a laser. Like, forget about the multicolors for a second. Let's say we have a laser that is one color. That laser enters the new medium and it either slows down or it speeds up, depending upon whether it's going from something like glass to air or air to glass. We're going to call this medium 1 and this medium 2. There is an index of refraction for medium 1 and there's an index of refraction for medium 2. In this case, we know that N2 will be high and N1 will be low. How do we know that? Look at the equation. How do we know that N2 is a big value there as compared to N1? Go ahead. Look at the relationship here. Theta 1, it's not a linear relationship because it's not theta 1, it's sine theta 1, but it's still proportional. Okay? Theta 1, theta 2, N2, N1. As theta goes down, N would go up. We can see here that theta 1, the angle of incidence we call it, is bigger than theta 2. Theta went down, N must have gone up. If it bent this way, right, theta 2 would be bigger than theta 1, and we would know that we were going from a high index to a low index. Let's go back to the original diagram here. What about speed? What do we know about the speed of the light in these mediums here? As we're going from medium 1 to medium 2, what happens to the light? Does it speed up or does it slow down? It slows down. Yeah. As theta goes down, what happens to V? Theta 1, theta 2, V1 over V2. As theta goes down, V goes down. Right? That's not a linear relationship again, but it's proportional. Okay? Theta 1, theta 2, V1, V2, N2, and 1. As theta goes down, N goes up because it's inversely related. As theta goes down, V goes down because it's proportional. Lambda would also go down, by the way, as well. So what do you see in this case here? If I simply draw this, we would know by the relationships in this equation, if theta is going down, it's decreasing in speed, it's decreasing in wavelength. Frequency, by the way, will stay the same. Frequency never changes once a wave has been made. The speed goes down, the wavelength goes down, and the index of refraction is going up. You got a higher value in the second medium than in the first medium. What do these different things mean again? Theta 1, theta 2, V1, V2, the speed in this medium, the speed in this medium, lambda 1, lambda 2, the wavelength of the EMR in the first medium compared to the second medium, N2 over N1, the index of refraction. That's increasing in this question. Yeah, I guess I did a few. All right, get a table in your textbook, guys. I'm going to ask you to memorize this for the quiz on Monday. I'm not. Your quiz on Monday, by the way, is on mirrors, not even on this stuff at all, right? It's on curved mirrors. Notice this table is obviously available in your book, and you'll get all the numbers that you ever need to get on a test or quiz, right? Don't need to memorize any of these numbers. Notice they're giving the refractive indexes, the indices of refraction for sodium yellow light. Like, what's the deal with that? Why are they specifying sodium yellow light with a wavelength of 589 nanometers? Why does that matter? Yeah, yellow's in the middle. Yep. Yeah, that's a good reason to pick yellow, right? But why don't they just say the index of refraction for each of these different materials? Because it's different for each color. Now, the reality is it's not that much different. Most times, we'll just be given an index of refraction for the material, regardless of the color. Because most times, we're not paying attention to the dispersion that's taking place. Okay, sometimes the dispersion takes place. We draw it usually with a prism because that kind of magnifies it because of the angles involved. But most times you don't get that much, if any, measurable dispersion. So most times you're going to be given just an index of refraction for whatever color of light it is. But strictly speaking, they should give it for specific colors because it's different, as Riley said, for each different color. The index of refraction in a vacuum is 1.0000. For air, it's 1.0003 because light travels a little bit slower in air than it does in a vacuum. I'll tell you what, though, usually we just drop those last two digits. In fact, on your data sheet, it says the index of refraction for air is 1.00. Okay, that's the number that we're going to use for air, 1.00, even though your book uses 1.003. That means that in a question, you might get an answer that's slightly off of the textbook, right? The reason that I want to use 1.00, instead of the number that they give us in textbook, is because I want us to be used to using the number that's on our data sheet, which is going to be what we're going to have for our exams. Right? No, it's 58, I think. Let's get in the habit of using the number that's on our data sheet. So scratch off those last two digits. You can see here that, look, glass, depends upon what kind of glass we have, it's around 1.5. Zircon, cubic zirconium, 1.92. Light bends more in cubic zirconium than it does in glass. Cubic zirconium will sparkle more than glass. It's more like a diamond. But it doesn't sparkle as much as it does in diamond, where the index of refraction is 2.42. This bends light a lot, more than any of these other materials. And as a result of that bending light more, we end up getting more sparkling, which people want, right? Because it's unique. Let's take a look at an example here on 13.3. Page 668. It says yellow light travels from water into crown glass. Water into crown glass. Water has an index of refraction of 1.33. We're going to call that N1 because it's going from water to crown glass. Crown glass is an index of refraction of, what is it, 1.52? So we're going to say N2 is 1.52. It's coming from medium 1 to medium 2. It's incident on the crown glass at angle 35 degrees. That's going to be theta 1. We want to find the angle of refraction, theta 2. So we're going to say, well, we could say sine theta 1 over sine theta 2, V1 over V2, lambda 1 over lambda 2, N2 over N1, or we can just say sine theta 1 over sine theta 2 equals N2 over N1. Solving for theta 2, a little bit tricky here. Goes up by multiplying. Trade places here, trade places here. We get sine theta 2 equals N1 over N2 times sine theta 1. Or theta 2 is equal to N1 over N2 times, sorry, it would be the inverse sine of that. Times sine 35. Okay, let's calculate this and then we'll be done for the day, for the week. Say sine 35. Let's get that number inside there first. Okay, multiply that by 1.33. Divide that by 1.52. Let's take the inverse sine of that. And we get 30 degrees. Should we expect an angle that's smaller? The index of refraction went up. Theta will go down. Okay, so is it right? I don't know, but we know that it's in the right range, right? We know that it's a smaller value. Okay, homework. Simply these 4 questions on page 668, please. Let's have those done for, let's have them done for Monday.